So now I am going to discuss Gauss's law for the dielectrics and electric displacement vector. And Gauss's law in dielectrics has two parts. One is this Gauss's law has two parts. One is the differential part or the differential form, and another is integral form. So first of all, let me talk about the differential form of Gauss's law. And during its Gauss's differential form, we will encounter a new term that we call that as the electric displacement vector. So to derive Gauss's law for dielectric, consider differential form of Gauss's law. Differential form of Gauss's law. So its differential form can be written like this, that del dot E is equal to rho over epsilon naught, where rho is known as volume charge density. It is known as volume charge density. Now in case of dielectric, if we consider the case of dielectric, then it has two types of charges. So first is volume charge density. Charge densities. So one is the volume charge density, rho f of free charges, and another is the volume charge density rho p of polarized charges. Therefore, this rho can be written as rho f over rho p. Now, this del dot E, it can be written as rho f over epsilon naught and rho p over epsilon naught. But this rho p, it can be written as minus del dot p. So if I put its value here, then I can write down it as rho f over epsilon naught minus del dot p over epsilon naught. And let us rearrange it. So it can be rearranged as del dot p over epsilon naught equal to rho f over epsilon naught right, and we can take outside 1 over epsilon naught here from here, so it can be del dot E plus rho dot p 1 over epsilon naught is equal to rho f over epsilon naught. So let us take del outside, so it is E plus p over epsilon naught is equal to rho f over epsilon naught. Then it can be written as del epsilon naught E plus p over epsilon naught, p whole upon epsilon naught is equal to rho f over epsilon naught, and here 1 over epsilon can be taken outside side, so I can write down it as epsilon naught E plus p is equal to rho f over epsilon naught. So this will cancel out with it. Then del epsilon naught E plus p over it is equal to rho f. So therefore let us define this new quantity, means this epsilon naught E plus P is equal to D, and this we call it as displacement vector. And the unit of D will be same as that of P, right? You have to keep this in mind, that the unit of P is same as that of D, right? So if I put this value here, this is a new quantity which we have defined. So if I define it, then I can write down del dot D is equal to rho f. So it is the differential form of Gauss's law. Differential form of Gauss's law for dielectric. And let us have a look at another way to look at this displacement vector. This may help you to do some numerical problems. Another way to look at displacement vector. D is equal to epsilon naught E as we have defined it, and let us put the value of this polarization vector. It is epsilon naught chi E. So that means it is epsilon naught E can be taken outside, so 1 plus chi E. So it is epsilon naught E, and 1 over chi E is known as K. As we know from earlier lectures that 1 plus chi E is equal to K is the dielectric constant. So therefore this D vector can be written and epsilon naught K, it can be collectively written as epsilon E, right, where epsilon is epsilon naught K is known as permittivity of dielectric. So this is another definition for electric displacement vector, right? So this is all about this differential form of Gauss's law. Now let us talk about integral form of Gauss's law for dielectric. Let me talk about the integral form of Gauss's law for dielectric. So consider the differential form of Gauss's law. The differential form of Gauss's law, as we have did, that is del dot D is equal to rho f. Now taking volume integral on both sides. Integral on both sides. So it is volume integral, it is del dot D into dV is equal to rho f dV, it's volume integral, and this tells us about the total free charge. Total free charge is represented by this integral. So I directly writing it down as a, because when I integrate the volume charge density, then it simply gives us the total charge, right? So that's why I'm writing it as QF. So therefore this volume integral del dot D dV can be written as QF. But let us recall Gauss's divergence theorem. Gauss's divergence theorem. So if we recall this theorem, then that indicates closed surface integral of some vector field is equal to the volume integral of del dot of that vector field, right? So if I use this here, then this can be written as this is equal to qf, right? So this is the integral form of Gauss's law. This is the integral form of Gauss's law for dielectric, right? So that's all for this lecture.